for joining us very o'clock, so at 1 p.m. This is part of a series of seminars that we are conducting as the Dutch section of the Combustion Institute. And this seminar will be recorded and will be posted on our YouTube platform. And therefore, if you don't want to be in your your face in the YouTube platform, perhaps it's better that you switch off the camera. And I have the pleasure, and I would like to introduce you to our speaker today, who is Anh Khoa. Anh Khoa has been, or is currently, an associate professor at the Aeronautics Department at the Imperial College of London, and a guest researcher at the Faculty of Aerospace Engineering at TU Delft, where he was an assistant professor until 2025. He obtained his PhD in engineering from Cambridge University in 2018 on the direct numerical simulation of mild combustion, and he has worked as a postdoctoral fellow at the TU Munich Institute for Advanced Study Mechanical Engineering Department from 2018 to 2021. He's also working as a group leader with the Cypher Cost Action on the hybrid physics-based data-driven modeling for reacting flows. And his research focuses on the development of scientific machine learning techniques for the prediction and control of extreme events in turbulence and turbulent reacting flows. In 2024, he was awarded an ERC starting grant for his project Context to further pursue this topic. Therefore, today he will be introducing us his talk titled Machine Learning-Based Approaches for the Control of Reacting Flows. Therefore, the floor is yours, Anh Khoa, and thank you all very much for attending, and I hope you like the talk. Thank you.
Thank you very much, Claudia, for the introduction, and also to Dirk and the Dutch section of the Combustion Institute for inviting me to give this seminar, and thanks everyone for attending this talk. So as mentioned, the title is Machine Learning-Based Approaches for the Control of Reacting Flows, and I would like to start by giving a bit the stage and the context of this research that I'm pursuing. So we know that in general, when we design a combustors, we basically design its geometries and fuel air conditions. And we have, for example, here the example of an annular combustor, but the way we design it is that typically we are going to design the fuel injection systems, the airflow systems, and the geometry of the combustor in such a way that we obtain a stable flame that has the appropriate efficiency and power generation characteristics. The thing is, like, once the combustor is designed, we basically have a combustor which is generally meant to operate in a relatively narrow range of fuel air conditions and operating conditions. And that means that these kind of combustors have a limited adaptability to operating outside of their design conditions or the conditions for which they were designed. So that's sort of the situation we're in. And I mean, in parallel to this, in relatively recent years, there's been some investigation in what I would call implementing some form of actuation available in combustors. For example, Pratt and Whitney are exploring the concept of adding steam injection into the combustors to improve the efficiencies of and stability of the hydrogen combustions. And for example, that suddenly gives us an extra degrees of freedom while the combustor is operating beyond just an air-fuel ratio or injection speed, for example. And so that, for example, here could be used to prevent potentially flashback, which is going to be one of the topic of the presentation of today. Another aspect that has been recently investigated by a colleague at Imperial College, so Andrea Giusti, is the potential of using oscillating electric field to control the trajectories of charged fuel droplets. That can then potentially give us some control on specific fuel stratifications, which is then also independent of which can be used and leveraged for different kinds of geometries. So that basically sets the stage for potentially having means to actuate the flame beyond, after the geometry has been set up. But the challenges of that, I mean, there are many challenges before we can actually do that, because we are encountering the natural challenges of turbulence and turbulence flames, where we know that their dynamics is extremely complex because we have this chaotic dynamics of turbulence, but also this interaction between chemistries and flow and turbulence, which basically is a complex dynamics to predict. In the context of future clean fuel, we have added complexity because hydrogen and also ammonia can exhibit what I call extreme behaviors. For example, hydrogen is susceptible to exhibiting flashback, and ammonia is susceptible to blow off because of its low reactivity. So my research and the topic of this presentation, and so this combination, of complexity in turbulent flames and in turbulent flames with sustainable fuel is that they would generally limit the performances that can be achieved using traditional control techniques. So the objective of my talk and my research in general is to leverage these developments in machine learning techniques to try to develop these control frameworks in this context of flame control, now that we have potentially some actuation possible in our combustors. So there will be 3 different topics. The first one will be on the development of machine learning techniques to prevent flashback using water injection, as I've already mentioned. The second one will be related to how can we develop machine learning techniques to control the fuel stratification that we obtain, the fuel stratifications if we have charged droplets. So that will mean how can we control and find optimal electric field parameters. And then the final one will be more on some numerical developments where we try to develop a differentiable flow solver that can act as a unified control development frameworks for flame control. So let me start with the first topic. So this one has been done in collaborations with Mitna, Pablo, and Ivan Angela from TU Delft, and also our collaborator at IASC, Aditya Konduri. Okay, so what do we look at in terms of flashback control? So we have these combustors. That means that, as I mentioned, I assume that I have some actuators which are available in my combustor. So that will be some water injection systems. And that also means that if I have actuator, I have to have an idea of when I should activate them, which means that I assume the presence of some measurements in our combustor. So ideally, as you can see from this video, the objective is that we want to activate our water injection system in such a way that it prevents this, the flashback from occurring. Okay, I can try to restart the video here. You see here there was some high temperature that appeared, and here the water injection flushed that out appropriately. But obviously that brings us to some questions in terms of measurements, which are, what do we need to measure so that we can anticipate the occurrence of flashback? And then if we can measure something that tells us that flashback is going to occur, that leaves us the question is, how can we design optimal actuators so that they flush out flashback in the most efficient manner? So the first point is going to be tackled by presenting some results on precursor identification techniques, or precursors of flashback identification techniques, which combines dimensionality reduction and clustering. And in terms of optimal design of water injection, that is going to be a Gaussian-based process, GPR, so Gaussian process regression-based optimization of the parameters of the water injection. Okay, so as you've seen, so in which kind of configuration did we do this study? We looked at a simplified model of the second stage of an Ansaldo GT36 reheat combustor. So that's a second stage. In the second stage of that combustor, what you have is that you have a highly preheated mixture in which and that second stage typically is going to be stabilized by autoignition. So you have this lean hydrogen mixture at relatively high pressure. And as I mentioned, it's reheated. It's heated because it's a second stage burner. And typically, this kind of configuration are designed in such a way that your inlet velocity here is, and the length of your duct here are designed in such a way that this heated mixture here will autoignite, but the autoignition delay time, it will only fully start autoigniting after the area jump, because you design the inlet velocity and the length of this duct here in such a way that the autoignition kernel only starts very much growing after the area jump. And then the autoignition kernel grows in size, and because you have recirculation, the flame stabilizes downstream here. So we perform simulations of these simplified geometries of what would be something similar to this second stage of this Ansaldo GT36 with combustors using LES and an 11 species mechanism. And then so here to summarize, that means that we have 17 different features in our flow, which corresponds at every grid points, the 11 species, the flow components, pressure, temperature, density, and that's it here. So what we observe in our simulations is that this combustor showed what we would observe as being intermittent flashbacks. So you had sometimes, despite having designed the length of our duct here and knowing the autoignition delay time of the mixture that we had here, the autoignition kernel would actually appear upstream resulting then in a kernel that would grow in your duct here and then entering the boundary layer, and that would mean that the flame would progress in your injection system. But then the burner could recover because you had a high inlet velocity, and so we had this intermittent flashback that would actually occur in this combustor. We could simulate that continuously, and so we collected a time series of 11 flashbacks and asking ourselves the question, well, can I predict what is triggering this flashback event? And then obviously, if I can find what is triggering those flashback events and what I can measure that can tell me that those flashback events are occurring, can we prevent those flashback occurring? So from our simulations, we just collected some time series in the burner. So here I'm going to present the study based on measurements collected here at the area jump. And these are just basically typical time series that you would observe. And if I look at the temperature field here, just leading up to the flashback event, you see that there's this large exquisite temperature, which occurs when basically the flame has moved upstream from this location point, because then you have exoscale. And as I mentioned, the objective of this first part is to identify precursors of this flashback, which means identifying the important features of my flow, which are related and which are related to flashback and which will indicate to us that flashback is occurring. And then once I have this kind of, when I know what are the important physical features to look at, I can try to find a set of specific quantities that tells us that precursor flashback is going to occur, and that means the precursors to this flashbacking event. So the first part is on with what is called co-kurtosis PCA, where we try to identify from all the thermophysical and flow states that we have, what are the ones which are relevant in this mechanism of flashback. So to do that, as I mentioned, we use co-kurtosis PCA, which is a method that was developed by our collaborator at ISC. And so what does it consist of? So co-kurtosis PCA, as its name indicates, it's first based on looking at the kurtosis. So the kurtosis is the fourth order moment. So that's related to the presence of fat tails in the distributions of your quantities of interest. The co-kurtosis, so now when you have multivariate distributions, multiple features that's related to whether multiple variables exhibit extreme values at the same time. And then you can apply PCA, so principal component analysis, or in flow, we often use POD, which is basically the same. We can apply PCA to your co-kurtosis tensor, and that the principal component of your co-kurtosis tensor are sensitive to the apparition of outlier. So just to illustrate this last point, here you have an artificial data set. So you have different circles which represent different samples, which have two different features, V1 and V2. And if you were to apply conventional PCA on this data set, you would have the full red line here as being indicative of your first principal component of this data set. And you can see that this data set has the majority of the points aligned here, but you have the apparition of this weird cluster, which would be these anomalous sets of states which are not present in your normal distributions of your system. So you could imagine these are when my system is evolving in such a way that, I mean, in what we would design it for, and here this would represent the apparition of your anomalous state. So obviously, the principal components, your normal principal components, are aligned with the direction of largest variance in this dataset, which is presented by this red line here. In contrast, what you can see is that the principal component of your co-kurtosis tensor for the same dataset here aligns itself with the apparition of these outlier quantities. So that really shows that the principal components of your co-kurtosis tensor are aligned with the apparition of the anomalous states, which we would relate to potentially this flashback behavior in this combustor. So once you have this direction of your principal component of your co-kurtosis tensor, you can project the original features onto that direction and identify which are the features, your original features, which align themselves, which contribute the most, to the direction of your principal component of your co-kurtosis tensor. So in this case, we would see that V1 aligns itself quite well with this apparition, which then would be indicative that actually V1 is a quantity which is relevant when we want to anticipate the apparitions of these outliers in my dataset. So these contributions of the original features to the direction of my principal component of the co-kurtosis tensor, we call them the FMM, which are feature moment metrics. Okay, So coming back to the data set that we had in terms of flashbacking events, we have all our thermochemical states that we sampled at a given locations. We can compute the co-kurtosis principal component for my co-kurtosis tensor and compute these FMMs, which here are presented here. So what this represents is basically for each different features that we have the evolution in time of their FMMs, so of their contributions to this principal component of my co-kurtosis tensor. And so if they take high values, that means they're highly contributing to this apparition of outliers in my dataset. So to walk you a bit through these figures, the important thing here is first, we could identify that pressure, density, and streamwise velocity contributed highly to my FMMs. So we could consider them as being important in this apparition of flashback. We also saw that O, OH, and H shows a very similar time series in terms of evolution. So that means that if you're just interested in terms of capturing the essential dynamics of those FMMs, keeping only one of them would be sufficient. So we decided to keep OH as a feature to be analyzed further. And then we saw a strong activity of the FMMs for HO2 and H2O2, which is somewhat to be expected, but as we know that both of them are precursors to flashback, to autoignition, sorry. So we also additionally kept temperature because it's an easy marker of telling us whether the flame has actually gone past our sampling locations. So that means that instead of having to analyze all the different quantities in my thermochemical states and flow states, we could just look at those sevens: pressure, density, streamwise velocity, OH, HO2, H2O2, and temperature. So that reduces a bit the analysis. So now we know what are the quantities that we should be monitoring, so those seven. How can we identify the specific combination of those quantities that will tell us that precursor is going to happen, knowing that potentially just setting threshold values might not be sufficient because we are in a turbulent environment, so you have natural fluctuations of those quantities. So to identify these specific conditions, we use the clustering techniques based on graph. So there were a couple of early stage, preliminary stage to be done. So first, from our time series of our quantities of interest, so the seven that I've mentioned, we can plot them in a 7-dimensional phase space, so the evolution in time of those 7 different quantities. So here they are just projected in a temperature and pressure plane, but it's a 7-dimensional phase space. We can tessellate this phase space in sort of small regions, small hypercubes, and we can then estimate from the data that we have observed how often do I see a transition between one hypercube to another hypercube in this in the observed data set. So what you obtain from this analysis is what is called a transition probability matrix, where basically the element ij indicates to you whether what was the observed probability of transitioning between a given hypercube I to another hypercube j. It's obviously going to be mostly a strongly diagonal matrix because within 2 consecutive time steps, your state has not evolved so much that you're directly moving towards another hypercube. So now that you have a transition probability matrix, you can interpret that as a graph where every node represents a hypercube and the edge represents the probability of transitioning between 2 different hypercubes. So now that we have a graph, we can apply clustering techniques dedicated to graph. And we use the techniques called modularity-based clustering. So the idea behind modularity-based clustering is to create clusters in this graph, which have a strong intra-connectivity and a weak extra-connectivity. So that means that it's going to create strong clusters that have many nodes which are strongly connected with each other. So a lot of edge among themselves, and very few edge with other nodes of different clusters. So the rationale behind using that is that when you have a set of normal states, you're going to keep on transitioning between normal states. So all those normal states and the hypercubes related to those normal states will be strongly connected with each other. The extreme states will be living by themselves because extreme states do not transition between one extreme to another extreme. And so those would be their own clusters. And in the middle, there will be a set of clusters which connect your normal large cluster to your individual extreme clusters. So now that we have then those precursor clusters, we can post-process them and use these precursor clusters as indicators of whether our system is moving towards an extreme event. And we can post-process that. So doing this, applying this to this data set that I've presented of these flashbacking hydrogen flames. We had this evolution in the phase space. Again, unfortunately, we cannot present this in a 7-dimensional space, but you can see the projection here in a temperature and pressure field. What you have here is the evolution in time. At the bottom left, you would have your sets of normal cluster here. The different points colored by the same color belong to the same cluster. And the number indicates to you what is the center of my cluster. But anyway, so that's the clustering which has happened. And then what we can do is, okay, this was the cluster obtained with just the first pre-flashback event. We can then look, okay, for the subsequent flashback, in which I can collect these 7 thermochemical states, these 7 features, and look, okay, this is the value that I have at that moment. What is the cluster to which I am the closest? Identify that, and then depending on what kind of cluster that cluster has been identified to be, a normal, precursor, or extreme, I can just ascribe the state of my system to the type of cluster to which it is the closest. So this is what you are seeing here, where you have in time the background color. So this is just the evolution of temperature at the sampling location. And then the background color indicates to you in which kind of clusters I'm classifying my system to be. Background color blue means normal, background color red means extreme, that means flashback has occurred, and a color in between orange or yellowish means we are ascribed to be in a precursor cluster. And you can see that we always identified the system to be into a precursor cluster before the extreme event before the extreme state occur, and that means that we have these observations that flashback might occur. And you can really see here that it's not just based on a thresholding of, for example, the temperature values would not give you the same information, because sometimes we can predict precursor of flashback much more upstream. And here, for example, then in other locations where basically the temperature is occurs a bit later. So it's really based on this combination of the 7 different features that we had identified with co-occur to this PCA. Okay, so now that we have these precursor identification techniques, we know what to measure, so we can monitor the 7 states, and that means, okay, now that we know that flashback can occur at those moments, or that we have some lead time that tells us, okay, flashback is going to occur, how can we design a water injection system that runs flashback? Because obviously there's many different parameters that my water injection system can have, and not all of them will result in effectively preventing the flame from really moving back upstream, as you can see from this video here. So yeah, the question is, how can we design this optimally? So in these simulations, we consider water injection that has 4 different design variables. So that means the water mass flow rate, the SMD, so that's the diameters of your droplet, water droplets, and basically the cone angle around which you're going to inject some water. So then I said, well, the objective is try to optimally design this water injection. So that means that we have to define some performance parameters. In this study, we defined 5 different performance parameters. The first one being, well, obviously flashback had to be prevented. So that meant that the flame should not have moved excessively back upstream. We also had the thermal efficiency, because you want to inject water, but you don't want to completely decrease the power, completely ruin the efficiency of your combustor, because ultimately the objective is to generate some power. The evaporation rate of your water droplets, because you want to make sure that you're not carrying water droplets all the way outside of your combustor in the form of droplets, so they should be fully evaporated. Pattern factor is related to the uniformity of the temperature field at the exit of your combustor, because again, temperature inhomogeneities, we want to avoid temperature inhomogeneities, and in the context of hydrogen combustions, we wanted to minimize also NOx emissions. So those were our 5 performance parameters. And obviously, we still have a relatively complex design space, because all those values of water droplets can actually be, there's a wide potential range of values that the 4 design variables can take. So we designed this surrogate model. So to obtain this link between the performance parameters in these design variables, we trained a surrogate model. So how did we do that? We first generate a database of 20 simulations with different values of our design variables. So the range is presented here, and we basically populated this 4-dimensional design space with a latent hypersampling techniques, which sort of distributes the point efficiently in this design space. And we performed those 20 simulations, from which we computed those 5 different performance parameters. And then with this database, we develop a surrogate model for each of these performance parameters using GPR, so Gaussian process regression. In the interest of time, I will not get into the details of the process. And so once you have this surrogate model, you can then use these surrogate models to analyze the influence of those design variables onto those performance parameters. So these are called Sobol indices. So here, the way to interpret your Sobol indices is just if you have a high value, that means that this design variable is strongly influential in this specific performance parameters. For example, here we can see that the thermal efficiency is mostly influenced by the water mass flow rate, m.w here, and which is somewhat to be expected because the more water you're going to inject in your system, the more it's going to take heat away from your combustion, so that would actually affect your thermal efficiency of your combustors. So we can look at other performance and Sobol indices. So you can see, for example, that the NOx emissions are influenced jointly by your water mass fraction, the SMD, and the cone of your water of your injector, which again somewhat makes sense. NOx is only influenced by temperature. So if you inject more water, and depending on the diameters of your water droplets, they might take more or less heat, and also other aspects like pressure factor. But basically, all of this, well, you can analyze them, and from a physical perspective, this dependency that the surrogate model had captured somewhat makes sense. So that gives some confidence in using these surrogate models in trying to find an optimal design for our water injection systems. So we can use these surrogates and then just use to optimize the design variables based on this surrogate model, which is based on Gaussian process regression, which is much cheaper to estimate than actually having to perform multiple full high-fidelity LES simulations. So that gives us an optimal design for water injections, and I'd just like to then show what happens when you have that. So here, this is the simulation. This is the evolution of what happens in our flashbacking combustors during a flashback. So if you remember from the co-characterized PCA, pressure was indicated to be a strongly an important feature to look at in the context of flashback. So you can see that indeed what happens during your flashback events is that there seems to be this increase in pressure, which is related to some pressure being propagated, pressure waves propagating in our domain upstream, which then increase locally your temperature, decreasing your auto-ignition delay time, and that led to flashback. So once we activate this water injection system, this is what happens. Basically, along the same regions here, the water injection manages to basically damp this increase in pressure and prevents basically flashback from occurring. Okay, so that was this first illustration on how we could use machine learning techniques to identify precursors to flashback, and how to use machine learning to find a surrogate model for the water injection system. So now the second one is on machine learning techniques to control fuel stratification with electric field. This work was done in collaboration with Andrea Justi and Nav from Imperial College, and also my PhD, Babak from TU Delft. So this work is going to be presented at the symposium in Kyoto. So again, coming back to our problem, in general, when you have, combustors are generally designed for given geometries and conditions. And here we have the ability that after the geometry has been fixed, to modulate the oscillating electric field so that you can control the trajectories of your droplets, of your charged droplets, and that then potentially gives the opportunity of controlling the resulting fuel stratification that you have. So how was this, on which kind of, this work was done numerically based on a LES framework developed in the group of Andrea Justi, where we use this Euler and Lagrangian framework for W square. And so the droplets which are being injected in the domains are charged droplets of jet fuels with these characteristics here. And as I've mentioned, the trajectories of those droplets can be modulated with this oscillating electric field. So first, without even any control, we can try to analyze what happens in terms of fuel mass fractions when we have different values of this electric field. So this is an example of a base simulation that we had where the droplets are being injected at this location here, and they propagate under the influence of your bulk velocity. And for these specific conditions of magnitude of your oscillating electric field and the frequency of your electric field, you see this pattern of fuel mass fractions, which is oscillating because your droplets are basically oscillating under the influence of your oscillating electric field. And as they propagate downstream, they naturally evaporate, and then it creates this sort of mist of fuel mass fraction at the outlet. So you can play around with different parameters. For example, if you increase the bulk velocity, you have an increase in the wavelength in the streamwise directions of your fuel mass fraction, which is to be expected as your droplet moves faster in the streamwise directions. If you increase the frequency of your oscillating electric field, you see that the magnitude in the spanwise, so this is a channel flow, of the spanwise directions of your droplets decrease, and similarly in the streamwise direction, this also decreases, and you can see that it creates for a more uniform fuel mass fraction profile at the exit here. And if you compound the two effects, if you increase both the frequency of the electric oscillating field and your bulk velocity, you have a compounded effect of both. So this gives some, let's say, base physical insight into this mechanism. So from these simulations, we want to perform some control. As I mentioned, the objective maybe is to look at your fuel stratifications or to control your fuel stratifications coming out of this, if you want, premixing stage, fuel preparation stage. And so you need to define a target for control. And in this case, we basically define a set of fuel mass fraction profile at the exits, which we would consider as the ones that we want to achieve under the control of this oscillating electric field. So we define its families of fuel vapor profiles depending on two parameters, Y0 and delta. Y0 governs the width of this fuel mass fraction profile, and delta controls the steepness between of this transition between your fuel containing regions and the outer regions in the channel. Now that we have our given target, we have to define what is our control system, our control environment. And in this case, we use what is called single-step digital reinforcement learning to identify optimal control parameters for this oscillating electric field. So in SDRL, what happens is that you have a neural network which defines the policy which is going to define and set the parameters that your control parameters, in this case, the frequency and the magnitude of this electric oscillating field. The way it identifies optimal values is going to be through what is called a policy training. So what happens here is that you are going to give what is the target profile that you want. So you give two parameters, Y0 and delta, that defines to you a target profile. You need to measure what is the profile that you achieve, so YF hat here. The difference between the two gives you a reward, an estimate of what is called a reward function. You can just see that as being inversely proportional to the difference between the two. So if they are perfect, that means your reward is maximized. And then with these values of reward and multiple values of reward, it's going to approximate, if you want, the dependency and the relationship between the target profiles and the parameters of your oscillating electric field. The way it approximates that is through what is called different batch trainings of multiple simulations with different parameters and collect together the values of rewards and then identifies how to modify its policy to move towards higher reward. So again, in the objective here, we ultimately use this machine learning optimization techniques called single-step deep learning to then identify these optimal parameters of the oscillating electric field for some given parameters of target mass fraction profile that we want at the exit. So we can obtain then these maps, which gives us optimal values of E0 and omega, and which is presented here, but ultimately this is easier to interpret. So here you have different target profiles that we have defined, so that those are the ones in full lines with the parameters provided here. And in dashed line, you have the profile obtained using these optimal electric field parameters observed. And you see in general, the SDRL framework is able to achieve the profiles of interest. Obviously, there are some profiles which are less well reproduced than others, but those are related. But these are related to the limited control authority that we have with just 2 parameters for the electric field. So this is shown here in 2D, but in the proceedings paper, we also show how we extended this to a 3D configuration. Okay, so this was the second example of how we can use machine learning to identify optimal control in electric field certifications. And then very briefly here, I want to touch upon the development of a differentiable flow solver. So what you see, a commonality that you see in these 2 control frameworks that I've presented is that there's a long time delay between when you start your actuations and basically what you're measuring to check whether the actuation has had a strong influence. Here, it takes some time for water to actually reach your auto-ignition regions. And then here you have to wait for your droplets to actually go through the entire domain before you can collect the fuel mass fraction profile at the exit. And so that is generally challenging for many control algorithms because you have this long time dependency between when you start doing something and when you actually can measure the influence of that action. And that for machine learning can be extremely expensive because you have to accumulate information over a long time. So that can be extremely dependent. So to compensate for that, there's this series of solvers which are called differentiable. So what they are basically solvers that that are effective and efficient in terms of, and provide what would be called an algorithmic judgment. So the bottom line, and very simply, that means that if you have a differentiable flow solver, you have the availability of all the gradients of all your variables that are present with respect to other variables which are present in your solver. So that means that you have this gradient, which is easy to compute and cheap to compute. So in the context of a control framework, okay, there we go. In the context of a control framework, typically what you have is that your controller is going to set the values of your boundary conditions in your flow solver. And to optimize this controller, now that you have a differentiable flow solver, you have this availability of this gradient being available here, the gradient of your future flow state with respect to your controller network. And that gives the opportunity of naturally optimizing your controller, which can be represented by a neural network. So that's basically what a differentiable flow solver provides. So we use this into some canonical problems. So in this problem that we call a flame ship control problems, the objective was to find a controller that would identify the inlet velocity here that we would need to achieve if we wanted to go from this initial temperature field towards this targeting temperature field. So this is a standard Bunsen flame. We also did the same in the context of extreme events in the 2D Kolmogorov flow. So this is a non-reacting flow profile, the objective being the controller network here has to find an optimal forcing that would only be active before extreme dissipation events. And we show that we could decrease the occurrence of these extreme dissipation events in the Kolmogorov flow. But yeah, so this was just to briefly touch upon what can be done with a differentiable flow solver. But anyway, to conclude what we have seen some machine learning techniques that can be used to help in the development of control framework for flame controls, because now we potentially have actuators in my combustors. So we show this in terms of flashback prevention, where we use a combination of co-kurtosis PCA and modularity-based clustering to identify precursors. And once we had precursors, we use Gaussian process progression-based techniques to optimally design the water injection system. In terms of fuel stratification control, we showed how reinforcement learning could control the electric field parameters to achieve some desired fuel quantifications, and also have very, very briefly discussed how we can use differentiable flow solver to improve control strategies. But obviously, there's still a lot of work to be done. All the examples that I've shown you are shown basically everything has been developed separately. So precursors have been developed in one stage, and the control is developed in a different stage. And obviously, ideally, you would control everything in a unified framework, which could be done with this different flow solver. All the geometries that you have seen here are obviously extremely simplistic. So the move towards more realistic configuration is still to be explored, and also the robustness of the control techniques that I've shown to more complex environments, turbulence, and other things like that is still to be investigated. And well, that's it for my presentation. Thank you very much for your attention. If you have any questions, I'm happy to answer them now or via email. And if you are interested in this, I will open in this research a postdoc position in my group, and will be open soon. So well, thank you very much.
Thank you very much.